Better late than never. Let's get the recording started. Yes. Yeah, I did. But now at least we'll get the second half in. Fridays are kind of crazy. That algebra class is ending. So I'm making an excuse for why I forgot to do it. Yeah, I know. Okay, we'll get started here. This next section is talking about, we have a function of x and y, and we're going to calculate the surface area over a certain region. Now, in Calc 2, we talked about calculating the surface of the area of a surface of revolution, where we had revolved say a curve around an axis, and what we got was called a surface of revolution. And we had looked at some formulas for calculating that area of a surface of revolution. Now this time, what we're doing here is we've got a function z is equal to a function of x and y, and we are going to calculate the surface area that's directly over or above some region D in the xy plane. So here's what we're talking about with this. So that gray area there, that is our function of x and y, and it's, as I said, it's kind of hanging there in midair. And what we're looking at, or what we care about, say, in this particular problem, is we just want to know what the surface area is that's above this region that we're calling D in the xy plane. So otherwise, we're cutting off the rest of the graph. and we want to see how much surface area we have right above there. We'll come back to this in just a minute. All right, so what we do here is we divide that region D into sub-rectangles. We'll call them R, I, J. They have two subscripts because we have one subscript going along the X direction, another subscript that's going along the Y direction. And in each sub-rectangle, let X, I, Y, J be the corner of the sub-rectangle that's closest to the origin, to 0, 0. All right. Now what we're going to do then is, so here we have a sub-rectangle right here, Rij. Here's our point Xij that's closest to the origin. And what we're going to do then is project that up vertically until we hit our surface. So project this point up to the surface, and we get a point that's right on the surface. Let's call that capital Pij, and so x coordinate is xi, y coordinate yj, and its z coordinate is going to be the value of the function, because that's how the surface is defined. So that's our z coordinate. Now, every point on a surface has tangent lines going in either direction, right? X and Y direction, and they have associated with it what's called a tangent plane that approximates the surface. This is stuff that we had for the last exam, all right? So I'm going to just say this point has a tangent plane that approximates the surface. That approximates the surface near that point. So here, let's look at this thing here. Okay, back to this. Okay, we projected our point near 0, 0 upward. We got then a point that's on our surface that we're calling Pij. And what we're getting then from this point has a tangent, a plane, that goes, of course, infinitely in both directions, out from that point. And that tangent plane, when we're close to this point, that tangent plane isn't much different than the values of our surface, all right? Remember, we talked about linear approximations of a function. Well, that's what we were using, the tangent plane. Okay. Now, we're going to be using this square here in order to approximate the surface. We're going to call the portion of the tangent plane that's directly up from our sub-rectangle. So we project that sub-rectangle up, and that cuts our tangent plane into just a rectangle of some kind, okay? So we're going to give that a name, and we're going to call that little rectangle, that part of our tangent plane, delta Tij. So let delta Tij be the part of the tangent plane directly above the rectangle. Be the part. This is all leading up to the integral that we're going to arrive at. So be the part of the tangent plane directly above that Rij, that subrectangle. Now, this area of this rectangle approximates that surface area in that portion of the graph. So delta Tij approximates delta Sij, and that's the delta Sij is the surface area right above the rectangle. The surface area above Rij. So we get an approximation. So what we do now is we just add all these different approximations together. We get that double Riemann sum. So therefore, the area of our surface, the surface area that we're looking for, it's going to be the limit as m and n go to infinity of this double summation over both of our indices, where I goes from 1 to m, j goes from 1 to n, and we're summing up all of those portions of the tangent plane. Okay. Now, the thing is, in order to get a formula here, what can we know about the area of the tangent plane? Yes, Jordan? Okay, all righty. Well, spiritually. Okay. So here's the question. What can we know, or what can we hope to know about this area of that portion of the tangent plane? All right. Here's a little diagram that's going to help us. I think it's very clever. So here's our subrectangle right down here. Here's our Rij projected up, and here is that portion of the tangent plane that's directly above it. All right. Now, what we have here, and here's our point, Pij. Basically, we have two vectors that come out from this point. We call 1a and 1b. All right. Okay, they're going to have components. This A1 is going in the x direction. You see the x-axis is right down here. Our A vector is going in that direction. Here, our y-axis is down here. The B is going in the y direction. And they're sloping down from this point, Pij. Now, we know that these are tangent vectors. Tangent vector and tangent vector. Well, the slopes of these lines are, one's going to be the partial derivative with respect to x. The other one's going to be the partial derivative with respect to y. Okay, the tangent lines, their slope, in other words, that's how the surface is changing underneath that point. Remember, the tangent line in one direction gives us, that slope gives us is fx. The other one is fy. So if we have a surface here, we have a point on the surface, say this is the x direction, this is the y direction. This tangent line right here, its slope is equal to fx, the value of the fx, and this slope here of this one going in, going in the y direction is Fy. Okay. All right. Because they're going to mimic how the underlying surface is changing. So the surface is changing as Fx in one direction and Fy in the other. So since we can write these vectors like this, I can write them, this vector here, the A1, it goes in the x direction, but it also moves downward or upward along the z direction. It has no component in the y direction. No component in the y direction. So its vector can be represented like, this vector can be represented this way. The x portion of it can be the I, that's in the x direction. The change there is delta x. But then if the change in the x direction is delta x, the change in the z direction, up and down, is going to be the slope, f of x, times delta x. That's going to be the amount of change in the z direction. All right? So therefore, A can be, the vector A can be represented like this. We have no y component, as an I and a j. The B vector has no x component. So we have a j component and a k component. If we let the j component be equal to delta y, then the change downward or upward in the z direction is going to be delta y times the partial derivative fy. So we get that B is equal to this vector. You say, well, why am I doing this? Well, remember this fact. If we have two vectors like this, A and B, and then we just complete them like this, where we repeat the B vector and the A vector, the area that we get there is equal to the absolute value of the cross product of the two vectors. So the area, this is a parallelogram. Its area that's caught between those two vectors is equal to the magnitude of the cross product of A times B. So what I'm doing here then is I'm going to try to figure out what this area is of that tangent plane segment. Well, it's going to be the cross product of A times the B vector. So what we do is we put in the A cross B here. We remember that A cross B is we do that determinant, right? I, J, and K. We do the two components, the components of A and B, and do the determinant. Okay. Once we've done that, we plug in these values in to our components, get the determinant, and then get the magnitude of what we get. Oh, right. What we finally get then is this, that the area of that tangent plane there is equal to this formula right here. The square root of the fx squared plus fy squared plus 1. So let me write this down here. Scoot it up or down? Down. Yeah, there's the A vector right there. Delta x I plus fx delta x k. B is delta y j plus fy delta y k. So this is what we get then. Oops, here we are. So what I can say here then is that our surface area is equal to the limit as m and n go to infinity of this Riemann sum, double sum, I equals 1 to m, j equals 1 to n. Now, in place of delta Tij, I am going to put this new formula that we have. So delta Tij is going to be the square root of fx at the xi, y, j, and that's going to be squared plus the fy at xi, y, j squared. Then there's a plus 1 under the radical, and then it's multiplied by delta A. Okay. And delta A, by the way, is equal to this is the area of the subrectangle. This is the area of Rij, the subrectangle. All right, so we know that the limit of a Riemann sum gives us an integral. So this is the final product here of all of this. I can then say the surface area is equal to the double integral over our region D of the following. The square root of fx squared plus fy squared plus 1 dA. All right. So I'm replacing, again, the summations with the integral signs. I'm replacing delta A with dA. All right. And let me put a nice asterisk here by this formula for the surface area. All right. Another way to write this formula is just using the Leibniz notation, double integral over d of the square root of, let's put the 1 first, 1 plus delta z delta x squared plus dz dy squared dA. All I'm doing is just writing the fx and fy using that other notation. Okay, this is actually very similar in appearance to the arc length formula from last semester. The arc length formula, remember that gave us the area of, the length of a curve. And let's recall this, we call this L, and this was the integral from A to B of the square root of 1 plus dy dx squared dx. So actually, this surface area formula here is really like an extension into another dimension of the arc length formula. So this is just the length of a curve. This is the surface area of a part of a surface. We have the square root in both formulas. We have the 1 in both formulas. But in the surface area, we have the squares of both the partial derivatives. In the arc length, we just have the single derivative squared. So there's a similarity in the formula. All right. So what I want to do next then is just do two examples of this. Okay, example 1. Find the surface area of z equaling x squared plus 2y, that's over the triangular region, that's over the triangular region D that has vertices with vertices 0, 0, 1, 0, and 1, comma 1. All right. What you need to do here is you need to draw the D draw the D region. All right. Okay, what are our vertices here? There is 0, 0, so this is y and x. We're given 0, 0, 1, 0, and 1, comma 1. So this is our D. Okay. So what we're doing here in this problem, we're taking this thing, we're just projecting this triangle up, and we're cutting off our surface where the triangle ends. All right. In fact, I've got a little diagram of what this thing actually looks like. Here's our XY plane right here, and then this is our triangle. This is, of course, 0, 0. This is 1, 0, and this is 1, comma 1. So that's our triangle in the XY plane. This is our surface here that we're given, z equals x squared plus 2y. And so this is the portion of that surface that is strictly directly above the triangle. And then it gets cut off. Okay? So this is what we're trying to calculate, the surface area of that right there. All right. So what we have here is we're going to have we can just write it out like this to begin with. We're going to do a double integral over D of what? Well, let's see. It's going to be the square root of 1 plus dz dx squared plus dz dy squared dA. Well, let's see. What is dz dx? Z is equal to x squared plus 2y. So dz dx is 2x, right? Y is a constant. And dz dy, x is a constant, is equal to the number 2. So we have this double integral over d of the square root of 1 plus, well, 2x squared, that's going to be 4x squared, plus dz dy squared, that's going to be 2 squared, which is 4, dA. So this is going to be the double integral over d. We combine 1 and 4 is 5. 5 plus 4x squared dA. All right. Now, we have to do this as an iterated integral, so we have to get our limits here of integration. All right. Would it be easier to do this first with respect to x and go horizontally, or might it be easier to go vertically with respect to y first? It will be easier to go vertically with respect to y. I'm not sure if you were just guessing with that, but that will be easier. Let's set this up here. First of all, okay, if we're going to go vertically, our bottom limit for y here is y equals 0. That's the bottom of our arrow. What's the top of our arrow going to be? How can I describe as an equation that straight line? Yeah, it's going to be y equals x. The slope certainly is 1 because it goes from 0, 0 to 1, 1, and the y-intercept is 0. So that is y equals x. So what we're going to have here, we're going to go first from y equals 0 to y equals x, of the square root of 5 plus 4x squared dy, and then, then we have to do our dx, and then what values does x range over? 0 to 1. 0 here, 1 here. You have to always draw these diagrams. All right. Now, this actually can work out fairly well. Let's do this integral here, the inside integral. With dy, that means that x is constant. That means this whole square root thing is considered as one big constant, because 5 is a constant, 4 is a constant. So what would be my antiderivative here? Yeah. Y times the square root of 5 plus 4x squared. Very simple. And then I'm going to evaluate that. The bottom one is y equals 0. The top one is y equals x. And then 0 to 1 dx. All right. And then we plug in our top and bottom values. Well, the bottom value is going to cause everything to be 0. So I just plug in the top value, and I get x times the square root of 5 plus 4x squared. And that's going to be from 0 to 1 dx. Okay. All right. Now, I need to evaluate this. So I'm going to do a u substitution. And it just happens to work very nicely. I'm going to let u equal 5 plus 4x squared. So therefore, du is equal to 8x dx. Now, I have an x dx, so if I want to divide both sides by 8, I get that I can replace x dx with 1 over 8 du. All right. Since this is a definite integral from 0 to 1, if I want to, and I think I'm going to do it this way, I'm going to go on and change my limits of integration and just keep everything in terms of u, and not have to go back to x. Now you can go back to x and go to the original limits of integration, that's fine. But I'm going to do it this way. So when x is equal to 0, u is going to be equal to what? 5 plus 0, right? U is going to be equal to 5. And when x is equal to 1, u is going to be equal to 5 plus 4. U is equal to 9. All right. So I'm going to let that be my new my new limits of integration are going to be from 5 to 9. And then my integral is going to be what? Well, x dx I'm going to replace by 1/8 du, and this is the square root of u, or u to the 1/2 power. So I just evaluate that integral. So I have 1/8 times u to the 3/2 power, divide by 3/2, that's the same as multiplying by 2/3. And I evaluate this from 5 to 9. All right, so that's, let's see, I can divide a 2 out from there. So I get a 1/12, and then it's going to be 9 to the 3/2 power minus 5 to the 3/2 power. 5 to the 3/2, I just want to leave it like that, but 9 to the 3/2 actually equals a whole number. And what whole number does 9 to the 3/2 equal? Yeah, it equals 27. The square root of 9, which is 3 raised to the 3rd power. So this is 1 over 12 times 27 minus 5 to the 3/2 power. And that's our answer. That's our surface area. So we had to do a U substitution with this one. Now, I want to point something out here, how important sometimes the way that we integrate can be. Let's suppose that I didn't realize at first that this was the best way to go, and instead I opted to do it as this way first, where I went horizontally with respect to x, all right? So if I did it that way, my bottom part of my arrow is x equals y. My top part of my arrow is x equals 1. Then I have what I'm integrating, which is 5 plus 4x squared. And now I'm going to first be integrating with respect to x. That's my inside. My outside is going to be y is going from 0 to 1, dy. So therefore, if I make the unfortunate choice of this being my inside integral that I need to do first, x is no longer considered a constant here, and I get the joy of figuring out this antiderivative. All right. Now, I just have a few things here, and I am certainly not going to go through this in detail, but here's just a few little bits and pieces of the work involved with that, if you do it by hand. All right. You end up having to you have to draw out a square root of 5. Then you have to let the tangent of u equal 2x over the square root of 5. This is from that really fun section there with trig substitutions. And we go on and on and on. We end up having to do the antiderivative of the secant cubed, which is this formula right here. And we plug things in, and we plug stuff in, and it's a real mess. All right? Now, I did this on Maple. Where's my Maple thing? Oh, here it's on the first page. I did this on Maple, and on Maple, you get the same, but you certainly would hope that you get the same answer that we got, and you do. This is actually the same answer as what we had gotten. Okay, they just distribute the 12 and reduce the 27 over 12 to 9 over 4. But you can get this antiderivative of 5 plus 4x squared, and this is what it gives you, and I was evaluating it from a to 1, and then I plugged this in from 0 to 1, and I got my answer. So I think this is a very good representation of one way it's fairly easy, the second way it's horrific if you're trying to do it by hand, all right, unless you're plugging it into a computer system, all right. So the way that you go, you get the same answer, but one way can be really bad. Any questions or comments on that? I thought that was really interesting how different it is, depending on how you do it. Okay. I just have one more example here with the surface area. And so here's our second example. Find the area of the portion of the paraboloid, and that's given by z equals x squared plus y squared, that lies under the plane z equals 9. All right, so this one we can draw a diagram for, and it won't look too horrible. Here's x, y, and z. Now, right here, this is where z is equal to 9. So this thing, you have to carefully read this, that lies underneath the plane z equals 9. So right here, we would have this plane that goes in both directions where z is equal to 9, okay? Now, this paraboloid, basically when x is 0 and y is 0, z is 0, and then as x and y continue to increase, this thing goes out like this, goes out like this, and it forms a circle up here, okay? This is what it looks like. So this is z equals x squared plus y squared. All right. So right here, this is this and also what's behind it. That's the surface area that I want to calculate. Now, what we have to figure out with these things is, what am I going to be integrating over? And that happens with practically all of these problems. What am I integrating over? We need to, again, draw the D picture. That's in the XY plane. Now, what we're talking about is, we're talking about taking this area here and projecting it straight down onto the XY plane. So we're going to have a circle here, and it's also going to circle around on the back. Now, right up here is where, this is where z is equal to 9. So that means that at the top, x squared plus y squared from my parabola equals 9, right? Because that's what z is. So this projection down here on the xy plane is the circle x squared plus y squared equaling 9. So draw that projection. So here's our y and our x. We're going to have a circle of what's the radius going to be of this circle? 3, right, because this is r squared. So let's just draw a circle of radius 3. Right. This is our D that we will be integrating over. Okay. Let's hope we can get this finished. So let's set this up. First of all, let's just set it up this. We're going to have a double integral over D. Okay, what's it going to be? It's going to be the square root of what? Z is equal to x squared plus y squared. So it's the square root of 1. Don't forget that. Plus, okay, z with respect to x is 2x. So I square that. That's going to be 4x squared. Z with respect to y is 2y, and I have to square that. That's going to be 4y squared dA. Okay, that's my surface area formula. Okay. So look what we have here. We're going to be integrating over a circle. And notice what we have here. This can be rewritten as 1 plus 4 times, in parentheses, x squared plus y squared. Could we benefit from using polar coordinates for this integration rather than sticking with rectangular coordinates? I hope we're going to say yes to that, because rectangular coordinates could be quite a daunting task But polar coordinates, this thing, because it's a circle, we have x squared plus y squared, it basically cries out for the use of polar coordinates. All right. Now, let's figure out our double integral here over d. So remember, for polar coordinates, we have theta and we have r. Those are our two coordinates. Theta is, what's that going to range from? In order, we want to cover all of this d. 0 to 2 pi. Our r is going to range from what to what? 0 to 3. Okay. Now, I need to write my function in terms of polar coordinates. So I'm going to write, how is this function going to be rewritten in terms of polar coordinates? The square root of 1 plus 4r squared. Because remember, r squared is equal to x squared plus y squared. Now, also remember the hardy har thing, r dr d theta. Don't forget that extra r there. Right. Okay, now we're ready to do this. And so we're going to go inside out. So for the inside one, I need to use a u substitution. So I'm going to let u equals 1 plus 4r squared. du is 8r dr. And thankfully, I have the r dr already. So let's just divide by 8. And I get 1/8 du is going to replace the r dr. All right. I'm going to, again, stay with my u here and just keep everything in terms of u. So here I'm starting when r is equal to 0, u is equal to 1 by plugging it in there. When r is equal to 3, u is going to be 1 plus 4 times 3 squared, which is what? That's 4 times 9, 36 plus 1, u is 37. So I'm just going to replace my limits of integration and stay with u. So this is from 1 to 37. Okay, r dr gets replaced by 1/8 du, square root of u to the 1/2 power. That's my inside. I still have my outside 0 to 2 pi d theta. And then this inside one is easy to do. It's going to be 1/8 u to the 3/2 divided by 3/2, which means I multiply by 2/3 from 1 to 37, 0 to 2 pi d theta. All right. So what I have here then on the inside is 2 over 24, that's 1 over 12 times 37 to the 3/2 power minus 1 to the 3/2 power minus 1. And then that's all within 0 to 2 pi d theta. Okay. So what am I going to get then for with this? I just have numbers on the inside. So it's all, yeah, certainly all a constant. So therefore, this is going to be, do we all understand that this is going to be 2 pi times 1 over 2 times 37 to the 3/2 minus 1? So this antiderivative of this is going to be 1/12, 37 to the 3/2 minus 1 times theta. That's my antiderivative there. And then just plug in the 2 theta values. So this is my answer, which for my surface area. Of course, I can simplify and make it pi over 6 rather than 2 pi over 12. So this thing certainly is something that if you want to be aware of when you can use polar coordinates, when you have circles that you're integrating over, that's usually your big clue that you want to use that. One other thing I want to just point out here, and this is actually right up here at this level right here, this double integral. This thing right at the start can be separated like this. Notice I don't have any theta in this inside integral here. I don't have any theta at all. This can right away be separated as 0 to 2 pi d theta times the other single integral, 0 to 3 square root of 1 plus 4r squared r dr. So I can separate it out like that just from the get-go. And of course, this 0 to 2 pi of d theta, that's the 2 pi that I got at the very end there, all right? This actually kind of simplifies the process, because notice otherwise I had to keep carrying down 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. That way I'm finished with it early on. Okay, so that's surface area using that formula, and so that's all we need on 15.6. What we get to start out with on Monday, and of course we'll only get a start on it, is triple integrals. And that can be a little challenging, but so something to look forward to, perhaps. Have a good weekend. Yes, sir.
So when you come out to this, and then you have to take the third that you roll that again, so you get
What was your,
well, I did a tabular integration with this, and so that.
This is, okay, is this your antiderivative?
Yes. Natural log of 1 plus x1.
Okay, let's look at that.
Oh, that's actually on the board.
Because Cassandra was asking about this question. All right, so our inside integral is dx. So y is a constant. Okay, now, what I did is I just went aside here, and we use integration by parts, which is that tabular stuff that you're talking about there. And let's see what what did you come up with? Well, let's see what I come up with here with the u times d. I come up with 1/4 x, not 1/4, 1 over y.
Right, I can see the y is right.
Yeah.
I don't know if that actually
It might not, just because y goes from 0 to 1. You could just luck out with that. But 1 over, I get a UV, 1 over y, 1 over y times x, ln of 1 plus xy, minus, let's see, VDU is what? Okay, 1 over y. Du is just to that first, and then 1 over d, 1 over y, ln of 1 plus xy. So this is going to be, this is u times B, X times 1 over Y L that minus B mu, which is 1 over see that, and then this is going to be minus 1 over Y. I don't there, but it's only zero here. U B. Oh, then I have to do